program this morning and in the afternoon. I want to urge you to come in tomorrow in the afternoon as well. There is one change in the afternoon session. There is just change of schedule. Tom Ruwitz will talk fourth, and John Elliott will talk first because of a conflict that he has with another session. Otherwise, the session will go on as scheduled and announced. The first speaker is John Hanson, and I don't know how many of you do not know John Hanson. He is a past president of ACI, past president of Jenny Elsner, board member of Jenny Elsner still, and he's a past president of International Association for Bridge and Structural Engineering, and he is a structural consultant foremost. John, please. He will talk about guarding against catastrophic failures in evaluating the structures. Please welcome John Hanson.
Thank you, Pete. When Pete asked me to make a presentation today, I was very happy to accept because it gave me an opportunity to come to Vancouver. I think this is a very beautiful city here, and I spent the weekend across the Malaspina Strait at Half Moon Bay, and it was certainly a very enjoyable time and gave me a even better appreciation of the Pacific Northwest. Well, I suspect just about everybody in the crowd here has had an opportunity to make a field evaluation of a structure or just an evaluation in general that has included a field inspection. And often we as engineers carry out these inspections in what we think of as a limited sense. We believe that when we do that, that really is sufficient to give us an opportunity to say something about the integrity of the structure. That's in contrast to an in-depth inspection where we have the opportunity to go into the structure in greater detail. But if a catastrophic failure should occur after we've made a limited or even an in-depth inspection, there is that possibility of some legal action against us. And I remember a case when I was president of Jenny Elsner Associates, when we had been making periodic inspections of a structure for a certain owner because of its very badly deteriorated condition. Well, one day, very unexpectedly, a portion of this structure collapsed in its quite significant collapse. In fact, the owner wasn't upset with us. He retained us to investigate the cause of the collapse. He retained us to design a repair for the structure. And in this course of this investigation, it was found that there had in fact been a very significant error made in the design of the structure. Well, subsequently, the owner even continued us to work on other parts of the structure, doing other work for them. But when the owner finally got around to asking the insurance company to pay for part of the cost of the collapse, well, the insurance company turned around and sued us because they thought that we should have caught or detected the collapse during the course of our inspections. Well, at that particular time, we were owned by another corporation which did not want publicity from a lawsuit. And I remember going to a settlement hearing for that suit, and the insurance company's lawyer at that settlement hearing, which was attended by quite a number of people, he asked me some questions, and he said, "Mr. Hanson, did your engineers observe the region which collapsed before, during their inspection?" Well, my answer was yes, and immediately the lawyer said, "Thank you," before I could express any explanation of it. He went on to say, "Mr. Hanson, did your engineers have the drawings for this structure when they were making their evaluation?" Well, I said yes, and just like that, he said, "Thank you, Mr. Hanson." Well, he then asked me another question. Mr. Hanson, was the error that was responsible for the collapse shown in the drawings? Well, my answer was yes, and of course I got that immediate thank you. At that point, the lawyer said to the group, he was very confident of achieving a significant settlement if this went into a trial or something like that. And after due consideration, our parent corporation at that particular time decided, well, they didn't want the publicity or the trial, and so they decided to settle. I always felt that it was something that really should have been fought even irrespective of the outcome. But in short, then, I think that whether simply to avoid potential liability, or of even more concern, I think, to all of us, to be able to believe that we're not to blame for loss of life or a very serious accident, we need to always be on guard for conditions that might indicate the potential for a collapse. I'd like to begin with this partial listing of major structural failures, and I emphasize it's a partial listing. Many more could be included. I'm reasonably familiar with most of these. In fact, I've investigated many of them. Some of them, while most of them are in fact collapses, some of them are involved with either a long delay in construction or significant disruption of service. Now, even though this listing will not include many failures that you're familiar with, I'd invite you to consider those that you are familiar with among those listed and see if you will agree with some of the observations that I intend to draw from these failures. You can see that I've divided the failures into three groups: bridges, buildings, and other types of structures. They're also divided into four categories according to age. That is, embryonic or under construction, young from about 0 to 5 years, middle age from 6 to 25 years or thereabouts, and old over something like 25 years. Each failure listed is identified by a name that it is commonly known by, and the year in which the collapse occurred, and in parenthesis, CS or W for concrete, steel, or wood. Now, most of the major failures in the first category, the embryonic category, have occurred in concrete buildings, notably the collapse of the 4-story flat plate Harbor K apartment building in Florida in 1982, the collapse of 24 floors of the flat plate Skyline Plaza apartment building just outside Washington, D.C. in 1973, and the collapse of the post-tension lift slab office building Lincoln Plaza in Connecticut in 1988. The failure of the jump lift forming system of the Willow Island cooling tower in 1980 was the worst construction accident in the history of the United States, and it killed 51 people. Failures have occurred in concrete parking garages as well in the embryonic category, including the collapse of a bay of the Crabtree Valley Mall parking garage in Raleigh in 1993, and the collapse of the Monroe Street parking garage in Chicago in 1981. Further, we've had many failures of concrete bridges during construction, including the collapse of the 3 spans of the post-tension Klein Avenue Bridge in Indiana in 1984, the collapse of a long span I-girder of the 12-Mile Creek Bridge in Kentucky in 1989, and the joint failure of the post-tension segmental Zilwaukee Bridge in Michigan. And even though they all have a distinct cause, the failures were influenced by the heavy weight of fresh concrete or low early age strength, which often requires as much engineering attention during the construction as is given to the final design of the structure. Simply being overly conservative in providing shoring or other support during construction does not offset the lack of critical requirements. There have been also numerous failures during construction of steel structures, which most commonly are due to instability or insufficient bracing during erection, and we've also had brittle fractures of steel structures, but I'm not going to go into these. The collapse of the 286-foot span of the Rosemont Horizon Stadium in Illinois in 1979 due to misalignments of the arches of up to 18 inches was also a major failure. On the other hand, most of the failures in the young category have occurred in steel structures. Notably, the collapse of the Hartford Civic Center in Connecticut in 1978, the sky bridges at the Hyatt Regency Hotel in 1981, and the roof of the Kemper Arena, also in Kansas City in 1979. All of those occurred under the first significant loading of the structure. They all also contained very significant deficiencies. The failure of the unbonded post-tension Dunnville, Ontario water tank in 1976 also attracted attention. I intend to use that as my first case history here in just a few minutes. There are fewer collapses in the middle-aged category, but failures have occurred in concrete structures in which long-term deformations due to creep, shrinkage, and temperature have caused a critical condition. The collapse of the precast, pre-tensioned roof system of an auditorium at Antioch High School in California would have been a disaster of epic proportions if it had occurred just a few hours earlier when that auditorium was entirely filled with young children. One collapse of a 15-year-old concrete structure for which the immediate cause may be attributable to corrosion of embedded reinforcement is that of the Cheyenne, Wyoming Air Terminal in 1975, but the opportunity for corrosion probably resulted from inadequate consideration of torsion in an edge beam of that saddle-type hyperbolic paraboloid shell structure. And as a result, there was excessively wide cracking, which allowed water into the cracks. Another collapse in this category is a bay of a precast pre-stressed parking garage, which I will use as my second case history, the North Memorial Garage. And finally, most failures in the old age category, are relatively equally divided between steel and concrete structures. The concrete structures include the failure of several bays of the Grant Park Underground Garage in Chicago in 1989, which I will use as my third case history if time permits. First case history then I'd like to look at is the Dunnville tank in Canada. So if somebody would block that.
What does F stand for?
What's that?
F stand for, you have steel S and C for concrete, and one of the bridges has F.
Foundation. I'm sorry. That was the Schoharie Creek Bridge collapse was a foundation failure. This is a view of the site after the collapse of a post-tension concrete standpipe. An aerial view, you see the concrete standpipe as the small circle in the center of the picture. That was a 50-foot diameter pipe. And I should note, I see Carl Peterson here. Carl and I were the ones that were out on the site of that very shortly after the collapse. This occurred in February 1976. The weather was very cold. The collapse was sudden and violent, and it sent debris throughout a 500-foot radius from the standpipe. Here's an elevation of that standpipe. It was constructed in 1974, so it was 2 years old at the time of the collapse, and the water depth was 116 feet. Here's a plan showing the standpipe. The buttresses for the post-tensioning tendons were located at the quarter points of the standpipe, and the tendons extended 3/4 of the way around the tank so that they could be overlapped 1/4 of the tank for each successive tendon as you go up the structure. The tank was slip-formed, but unfortunately the workmen walked off the job shortly after beginning the slip forming operation, and to keep the job going, the contractor went into town and recruited a number of very entirely inexperienced people to continuing the slip forming operation. Here's a view on the ground after the collapse, and you can see how the debris was spread out around the standpipe. Here's another aerial view. The closest person to this standpipe was on top, was on a fuel tank unloading fuel, and I guess I don't see that, but it was down in front of the standpipe about 100 feet away from it. This person, he was standing on top of his fuel truck. This person said that he heard a loud noise. He looked up, he saw the tank coming apart, said as he was standing on top of the tank that he was dodging the post-tensioning cables as they flew out away from the tank. And then he held onto the tank as a wall of water hit the tank, but he walked away entirely unscathed. I suspect that he probably had to go home to make some change in clothes, but at least he wasn't hurt. And here again you see another view of the ground, and you can see the large pieces of concrete that were thrown out away from the tank. Oops, did I go too far? Yep. No. This is a detail of the buttress, and you can note the number 4 U-shaped bars intended to prevent the buttress from separating from the tank. 1 bar was required by each tendon anchorage near the bottom, where the tendons were closely spaced. This is the anchor detail, and you see that there were 2 number 4 bars to be replaced just ahead of the anchor. But here you see a piece of the buttress out in the field of debris. The separation occurred in the plane of the post-tensioning cables, and you can see only 1 small piece of reinforcement going through there. Maybe there are a couple on the other side, I don't remember, but very obviously the bars, the hairpin reinforcement, did not get put into the buttress the way it was supposed to have been done. And as a result, there was this separation of the buttress in certain areas, at least, from the wall of the tank. Here's another view showing the anchorages and how then, because of the lack of the hairpin reinforcement, they were able to simply pull into the, and force the separation there, at least in certain places. Well, here's a piece of the buttress and the wall of the tank which did not separate, and it's a quite large piece, but we know that the failure occurred as the result of the lack of the hairpin reinforcement. But I guess the question is, why did this grossly deficient construction survive for 2 years before the failure? And I think that was due to the ability of tension in the concrete to sustain the stresses of the buttress. But then what was the likely trigger of the collapse? And you can see that in this slide here, because corrosion started at the anchorages of the post-tensioning tendons. Obviously, that's an anchorage where you see the rust stain on the outside of the buttress, and therefore that is the trigger, I believe, of the collapse, the start of corrosion in a region which was unreinforced, then the propagation of a crack which could not be stably contained, and a very catastrophic failure occurred as the result. But this is what you would have seen had you been looking at that tank just a short time before the collapse occurred. The second case history is this precast, pre-stressed parking garage in a suburb of Minneapolis. You see here a view of the helical ramp and the 6-tier parking deck. It was constructed in 1972, the part in the foreground, and the lighter part of the structure, which is somewhat whiter, was constructed in 1982 in the background. In July of 1989, one section of this ramp immediately below the top level collapsed, as you see in this slide. Here's a plan view of the area where the collapse occurred. You can see that, or maybe not well, but I'll call your attention to the fact that the collapsed bay was at a location where there was a drive-through between the old construction and the new construction. The double T beams in this area had a length of 57 feet. Here's another closer view of the end of the bay where the collapse initiated, and the double T beams were supported on a spandrel beam, which extended from the one column you see in the background here to the column on the left side of the picture. Here's a drawing of the spandrel, and it was supported by a bearing pad at the reaction and also 2 pads against the column. Here's another view indicating where those reaction points were located. The pads taking the primary loads were shown in the preceding slide, but we should be well aware that volume changes may impose additional forces at these reaction points, which can be quite large. Here's a view of the end of the spandrel, and it doesn't show up well on this, where it fell on the lower deck. Here's the end of the spandrel right here. This is concrete that was the curb on top of the double T beams. This is the end of the double T beams at this location. The spandrel beam was taken to a storage yard where it could be examined much more closely. And a piece of concrete was found at the site, which you can see perfectly fit into the end region of that spandrel beam. Now this is that same piece of fractured concrete taken back to the structure and set in place on top of the column. And it is very evident here that there has been both rotation and movement of the spandrel away from the column, and also that the bearing pad was badly disintegrated due to volume change forces and to repeated loading from the crossover traffic. Many early precast decks were built which relied on shear transfer through pads for stability and to accommodate volume change movements. And it is now recognized this was not good practice. And while many of these decks have been retrofitted or repaired, there are many others that I think this condition is still of concern. And in guarding against failures, I think that engineers need to be aware of this condition. I see I'm kind of in an in-between place here, so I think I'll try to quickly show this case history in abbreviated form here. This is a parking garage in Chicago, Grant Park Garage, and the failure began along this ventilation opening on a Saturday evening when part of the top of this underground garage dropped down, as you see here. A few hours later, it fell to the ground, as you see here. Here's a view of the debris on the top, on the lower floor. And another view. And here's a plan of the area that collapsed, the area in yellow. You can see that in that region, the framing is different than in the other regions of the parking garage where it was either a beam and slab construction or a flat plate, flat slab construction. This is a section through the area where the collapse occurred. In the beam and slab area, there was a cantilevered beam, which then picked up a wall or a posts, tension post, to hold the end of the one-way slab and carry it over to column line 4, where the wall beam took the reaction down to the columns below. This garage was designed in the 1951 ACI code, specifying concrete of 4,000 psi and reinforcement of 20,000 psi allowable stress. Here's the section through the area that collapsed, and you can see the picture. The failure is believed to have initiated in the cantilever beam on the left-hand side here. And here's a close-up view of that cantilevered beam. It shows why it partially collapsed. You can see the negative moment reinforcement in the beam that extended out to the end of the beam and then down to pick up the end of the one-way slab. And when the failure suddenly occurred, that reinforcement served as a tension tie and held the end of that one-way slab for several hours before the steel pulled out and allowed the entire bay to collapse. Now, here's a view of the drawings that were available on that structure, and they are hard to see, but this is the beam behind, this is the cantilever beam, and this is the beam behind it, the anchor main span. You can see it was labeled B256. You can see that the designer or whoever was doing the detailing didn't quite know what to do in this region, so he put B256, but he put it in parentheses. Then when it came to the table, is that B256? Yes. Okay, you can see that they called out the reinforcement in the manner that you would expect and typical for that time, where they detailed the location of every single stirrup reinforcement in number of inches from the center line of the column. But they didn't put the beam parenthesis B256 in the table. I would imagine they came to it, they had the table set up, and they didn't really know how to handle it, so it just got omitted. And as a result, this is probably what was the reinforcement. The most critical element, the cantilever beam, did not have any shear reinforcement in it. And it should have had very heavy shear reinforcement to prevent the collapse. You see the absence of the shear reinforcement here. Now, if that cantilever, after the debris is cleared away, you can look at that picture and decide this is probably what the crack pattern was that precipitated or caused the failure. And when that debris is stripped away, you see the dark colors there, which is seepage of concrete, water and debris down below. But then you can also then see how over time corrosion of this main reinforcement occurred in this region here. These bars now were very closely spaced. They're number 11 bars. They did not have any confining reinforcement, so I think that once corrosion started in that region and you started to drive a splitting crack, that it was just a question of time until, and in fact it took 30 years for the failure to occur. Closer view of that, you can see the rust and the imprints of the bars. And the collapse did not extend further because of the stairwell to the right, which served as a supplemental support and kept confined it. Now here is, let's go back to this one. The next cantilever over from G is H. I'll show that in the next slide. And the next cantilever over from that is the one at J. So here's the one at H. It partially failed, but did not totally collapse because of the stairwell. And the next one over, you see in the background there, has a little bit of damage to it. In fact, the white region there, I'm having trouble getting the picture from this angle. The white region on the bottom there was where some concrete flaked off, but you can see that the main crack is there but did not even open in the cantilever beam. And imagine this picture without that white region there, and probably without some of that other incline cracking. That is all that you would have seen had you made an inspection, in fact, of this structure in advance of this collapse. Well, why did that last for 30-some years? It was because the concrete strength was about 6,000 or 7,000 psi, and consequently the concrete contribution to the shear itself was sufficient to hold or provide for the strength of the beam. Okay, next go back to the view things here for my concluding remarks. Let's then now try to draw some observations from these failures and also from the table. Failures and collapses of middle-aged structures have occurred due to volume changes, shrinkage, creep, and temperature, and this phenomena did not receive sufficient attention in design for a long period of time. There are many structures with these design deficiencies, I believe, still in service, and we need to be on guard for that kind of condition when we make an inspection of a structure. All failures in the old category were in structures exposed to the environment and were due entirely or in part to the effects of corrosion. Corrosion of embedded steel has been the trigger for collapses also in young and middle-aged structures. The corollary, I believe, to this is that if a structure survives to an old age and is not exposed to the environment, it is going to have a very, very long life. Several of the failures occurred in structures that carried high sustained loads and tension. There's little opportunity for redistribution, and these kinds of failures have catastrophic consequences. We need to give these conditions very close attention. Oversights at interfaces between different types of construction, such as precast concrete and steel, have also been a source of many local collapses. You should be on guard for larger than expected movements at these locations, at these junctions. And finally, most of the failures can be attributed to large errors in design or construction. Or to be blunt, when you get down to the root cause of the failure, they're really blunders. Evaluators should recognize in making a condition assessment or the like that errors of the order of the magnitude of 20% rarely have a significant influence on the safety or serviceability of a structure. You have to be on guard for large errors of the order of magnitude of the safety factor. Thank you.
I think we're going to have two questions. There are, before we conclude. Any questions, please?
I think I answered
John
all.
will be around, you can answer some questions later as well. Thank you very much. Thank you, John.